Hello, my name is Rod Badicke from StreamSim Technologies, and this talk is about well rate allocation factors for reservoir pattern surveillance. In reservoir surveillance, a well pattern is a group of wells usually centered on a single injector, such as the inverted 9-spot patterns on the upper right. Regardless of how the pattern is defined, a required parameter is the well rate allocation factor, or WAF for short. The WAF relates the fraction of production due to a specific injector or fraction of injection to a specific producer. Once the WAF is known, this fraction of production, for example given by the formula below, is simply the WAF at P due to I times the total production rate Q at the producer. There are different approaches to computing the WAF. In this presentation, we will discuss a geometric method and a flow-based method. With a fixed pattern, the traditional approach to computing the WAF is based on geometry using the angle theta open to flow between the well pairs of interest. Thus, for the inverted 9-spot on the right for this specific IP pair, the producer WAF based on the angle open to flow is 1/4, while the injector WAF based on the angle open to flow is 1/8. Note that for one of the side producers, the production allocation would be 1/2. However, the limitations of the fixed pattern geometric approach are that the WAFs are not a function of the historical well rates. In other words, they are assumed to be constant. They do not account for well pair distances, and they are difficult to compute for 3D systems. Another way to compute WAFs is to use streamlines. Streamlines follow the velocity field in a reservoir and represent flow paths between wells. For 2D flow with vertical wells and homogeneous geological properties, the velocity field in the x and y directions is defined analytically as derived by Cottle. Here, Qi is the rate and xi and yi are the positions of well I. For an inverted 9-spot pattern with balanced production rates in green and injection rate blue, where injection is 8 times production, this, along with the well positions, defines the velocity field using the above equations. Next, streamlines can be traced following the analytical velocity field to give the final picture on the right. Along with streamline paths, each streamline carries a volumetric flux Qs. If we zoom into the upper left PI well pair of the inverted 9-spot and look at the streamlines in detail in the left image, we know the volumetric flux along each streamline at the injection and production sides. Next, to compute the allocation factor, for example on the production side, we sum up the streamline fluxes from the specific injector as shown in the top formula, then divide by the total production rate QP to give the WAF at P due to I. Similarly, on the injection side, we sum up streamline fluxes leaving the injector towards P in the numerator of the bottom formula. Dividing by the injection rate Qi gives the WAF at I towards P. Returning to our inverted 9-spot with equal production rates and computing the flux along streamlines between all well pairs, we compute injection WAFs of 12%, which is the same as the geometric case. For simplicity in the picture on the right, we collapse all of the streamlines into sticks and label each stick with the injection allocation factor value. We call this picture on the right the flux pattern map. Now we look at the same inverted 9-spot pattern with the same injection rate but different production rates and observe how the streamlines and the WAFs change. On the left, we have increased the production rate of a single producer and reduced other producers. Now the injection allocation factors for the same geometry range from a low of 4% to the highest at 44%. In the middle picture, we shut in the producer. Now injection allocation factors range from 12% to 19%. And finally on the right, we add an infill producer and observe that the new infill has an injection allocation factor of 16%, while the remaining WAFs range from 6% to 14%. In all cases, as the well rates change, the streamlines and hence the WAFs change. In practice, we cannot trace streamlines analytically in real fields, as reservoirs are 3D with complex geology and non-vertical well paths. Instead, we use a numerical method. Streamlines can be traced numerically in a reservoir simulator. We require a 3D grid, geological and PVT properties, historical well rates, and well paths. Then we solve the flow equations, in this case the pressure equation, apply Darcy's law to determine the velocity field, and then trace streamlines numerically such that they follow the velocity field. For real fields, when solving for the streamlines numerically, this can give what looks like a spaghetti bowl of streamlines on the right. However, if we then compute the WAFs from the known streamline fluxes, we can collapse this image into something more reasonable, which is the FP map. Now we see sticks having the same color share a common injector highlighting each injector pattern. Additionally, we label each stick with the allocation factors for these patterns. Thicker sticks indicate larger allocation factors than thinner sticks. Although not shown here, we could create the same FP map but centered on producers, showing the production allocation factors. An important concept when using flow-based WAFs is that each pattern is dynamic. Dynamic patterns have the following properties. Each pattern is injector-centered. The WAFs define which producers are in the pattern and the amount of flow to each producer. The WAFs and the pattern change as historical well rates change. In this example of a single injector displayed using the flux pattern map, the inverted pattern changes through time as a result of the changing well rates from January 2018 through to January 2019. Additionally, the allocation factors also change through these time periods. In summary, the WAF is a critical parameter needed to relate injection to production volumes in reservoir pattern surveillance. Geometric WAFs are based on pattern and well geometry. The limitations of geometric WAFs are that they are fixed in time until pattern geometry is redrawn. They are not a function of historical well rates, nor are they a function of geology or well pair distances. Flow-based WAFs can be computed from streamlines. They account for changing well rates, locations, and non-vertical well paths, as well as 3D geology. Flow-based WAFs automatically define each pattern, meaning that patterns are dynamic and can be injector or producer centered. In other words, regardless of the complexity of the flood, patterns can always be defined in a robust manner using streamlines. I'm Rod Badicke, and thank you for listening. If you have any questions, please visit us at streamsim.com or email us at support@streamsim.com.